For the first graph, you are plotting charge on the horizontal axis and voltage on the vertical axis. Your graph is to validate the expression Q equals CV, where V is the voltage, Q is the charge on the plates, and C is the capacitance. You're asked to go from negative voltage to positive voltage. This should result in charge values that also vary from negative to positive. The signs of the charge appear on the upper and lower plate, so make sure to include the numerical value of the charge as well as the sign on the upper plate as you change voltage from negative to positive values. Done correctly, this data set will result in a straight line graph. It should pass through the origin and stretch from the first quadrant to the third quadrant. Excel will give you the equation it used to produce the fitted line to your data. If you compare its generic equation to the equation we are trying to verify, the voltage represented by X and charge represented by Y, then that means that the slope must be the capacitance. The y-intercept, B, is the place where the fitted line crosses the y-axis. We are not concerned about this if it is quite small. Be careful with the value of the slope when comparing to the capacitance. If you plot the values as recorded for both the voltage and the charge, note that the charge column is in multiples of 10 to the minus 13. If you recall that the definition of slope is the change of y divided by the change of x, that means that your change values of y should be multiplied by 10 to the minus 13. So if you plot the data as recorded, make sure to multiply your slope value by 10 to the minus 13 when comparing it to your capacitance value. The second graph is a plot of capacitance versus area of the plates. The equation to be verified is this one. Plot capacitance on the vertical axis and area on the horizontal axis. Looking at the equation, this should result in a linear graph. The slope should be equivalent to the constant epsilon naught divided by the separation, since the separation was held constant this time. The graph should be projected to the y-intercept, and an equation that Excel used to create the fitted line should appear on the graph. You should be able to set the slope equal to the fraction epsilon naught over d and solve for epsilon naught, assuming all your data values have been put in SI units. The third graph to be completed is used to further verify the form of this same equation, except this time it is the separation that varies and a cross-sectional area that is kept constant. As can be seen, this means that a graph of capacitance on the y-axis and separation on the x-axis may not be linear. Initially plotted, you should get a curve fit. You will need to linearize this graph by adjusting the values of the separation that you plot. Have Excel create a new column of reciprocal separation values. Excel can give you the equation of this fitted linear line, and the slope can be set equal to the product of epsilon naught and the cross-sectional area to solve for epsilon naught. The fitted line should be extended to the y-intercept. Again, make sure the values used in creating the graph are in SI units. Excel can help with this as well. If you have the separation in millimeters, create a column beside it where you have divided all the separation values by 1,000. And if you leave the capacitance values as listed, don't forget to multiply your slope by 10 to the minus 13. Capacitance will be the change in y portion of the slope for comparison to epsilon naught. The last graph to be done attempts to verify the stored energy relationship. This should be a graph of energy on the vertical axis and voltage on the horizontal axis. Done correctly, the graph should be part of a parabola. The energy relation shows that the stored energy on the capacitor goes as the voltage squared. A graph that ends up being a parabola, or in this case half a parabola, is an indication that the horizontal data should be squared to linearize the graph. But this time you are not to complete a new graph after you linearize the data. In this case, use Excel's More Options under Trend Line to provide an equation that best fits the data, likely a power law fit. I attempted to use both a power law fit and a polynomial fit just to see what it might do, but use the power law fit option with your data. In the analysis section, you are shown a generic power law equation. This should allow you to identify what the numbers that Excel provides should be. B is some constant, which if we compare to the appropriate energy relationship, should be the same as the capacitance divided by 2. N is the power that the horizontal variable is raised to. MyFit gave N as 1.98, close to the horizontal value squared, and you can see that the constant B is equal to 0.4412. That should be half the capacitance once I make sure all adjustments are made for putting the equation into SI units. I have energy on the y-axis, so it is necessary to multiply the slope value by 10 to the minus 13 when it comes to determine the capacitance value from the value of the constant B in the power law equation. Finally, I had Excel do the different calculations asked for. In summary, we are going to have 5 graphs. 2 graphs are linear to begin with. One graph is initially a curve. The next graph will be the linearized version of this same data set. And the last graph is energy versus voltage, which should be a parabola, and the curve fit using a power law fit. All graphs should be stretched in Excel to fill a blank page in your Word document lab submission. There are different calculations that are asked for that come from the slope generated in the curve fit equations. The steps necessary to do those items should be completed on the calculations page or pages separate from the graphs. And of course, data tables and answer questions should also be included.